one way to go from liters to moles is by using the molar volume. The second way to go from liters to moles is by using the ideal gas law. N is equal to PV over RT. And so we need some additional information. Now the additional information that you're going to need is, you know, what is the temperature and what is the pressure? And so what do you think the most common temperature is? 25 degrees C. That's what we call room temperature. And what do you think the most common pressure is?
1 atm.
1 atm. And so what do you think the molar volume of the gas is? If it's not given, we have to make an assumption. Sometimes the information is not given. You say, okay, let's assume that we're dealing at 25 degrees C and 1 atm, which makes total sense. Do you want to assume that we're working at 0 degrees C and 1 bar? Does that make any sense? No, that doesn't quite make sense because of the, okay, uh-huh. 4.5, right. Well, that is a much more useful number to memorize. I had to memorize the other number, but that was a waste. That number is very useful because you can use it over and over again. So the basic strategy is what? Tell me what the basic strategy is. We're going to calculate for limiting reagent, we're going to calculate the yield from the initial what? Are you guys making progress or getting stuck on this? No, not in this one. With this one, we're only calculating the ideal yield, but it's a limiting reactant. It's going to be called the theoretical yield.
So we have to look at the one that's smaller.
Yeah, right. The smaller amount method, right? Two separate calculations, good. And so one is this. What do? We look at the yield from glucose, assuming we have plenty of air. And then we look at the air, yield from this much air, assuming we have plenty of glucose. And so we'll just do it here. Yield from glucose. And so glucose, we have 5.15 grams. Glucose. Then we need the molar mass of glucose. So 180.18 grams. That's good. 180.18 grams per mole. Is that what other people got?
Yeah.
Okay. C6, H12, 6. So grams of glucose canceled. That gives us moles of glucose. From moles of glucose, we want to go to moles of
Carbon dioxide.
So it's 6 moles of carbon dioxide for every 1 mole of glucose. So that gives us moles of CO2. Now CO2 is a gas. And so if we know the moles, we can go straight to the liters by using the molar volume. The molar volume we calculated in the previous problem, it was 24.45 liters per mole of gas. But you know, this molar volume is only valid at room temperature and 1 atmosphere. So gas at RT and 1 atm. But it's a handy number to remember because, or you know, even if you forget it, it's an easy one to recalculate. Just see how we calculated it. You can always recalculate it. And so we can calculate the yield from the glucose, which is going to be 5.15 divided by 180.18 times 6 times 24.45, 4.19. Actually, I could, I don't have to subscript. We know this to 4 sig figs is 24.45. 4.19. 3 liters of CO2. yield from glucose. Now we have to do the yield from air next, and then compare. We'll pick the smaller amount. Let's do the yield from air. So how much air do we have? We have 10.0 liters of air. Well, we don't want air, we want oxygen. And so how much oxygen is there in 10 liters of air? Well, here we're given the percent by volume. Right? So if I had 100 liters of air, I would have 20.946 liters of oxygen. And so what we can say is that this is just a percentage. For every 100 liters of air, I'm going to have 24.946 liters oxygen. This is for dry air. It's from Wikipedia. And so air is not pure oxygen, so it's about 20. It's about 20% oxygen or 21% oxygen. 21% oxygen. I just kept it 80-20 to keep the numbers simple to remember. That air is 21% oxygen. Okay, roughly. But that gives us liters of oxygen, and then from liters of oxygen, we could go to moles. Or alternatively, we could go from moles of air, like this. This percentage is either volume percentage or mole percentage. If we were given the mole percentages, then I would have went from liters of air to moles of air. How can I go from liters of air to moles of air? The molar volume. It doesn't matter if it's a mixture or pure, it's a gas. And so I can figure out how many moles of air I have. And from moles of air, I can go to moles of O2. But since this is a percent by volume, we'll just leave it as percent by volume. And so now I have liters of O2. Where do I want to go now?
Moles.
To moles. Right. Since it's a gas, I can use the molar volume. A mole of O2 or any gas is going to occupy 24.45 liters. And so that takes us to moles of O2. Liters cancel. And then from moles of O2, I'm going to go to,
Moles of CO2.
yeah, so 6 moles of CO2 for every 6 moles of O2. And then from 6 moles of CO2, I'm going to go to,
Moles of CO2. Forget CO2. And then 1 mole, 24.45 liters.
yeah, I'm going to go from moles of CO2 to liters of CO2. And so moles of O2 cancel, and moles of CO2 CO2 cancel, and that leaves us with liters of CO2. The 24.45 cancel, the 6 cancel. So let's go ahead and do that calculation here. So this is going to be 10 times 20.946 divided by 100 equals 2.09. .094 liters of CO2. And so what is the theoretical yield of CO2 in this combustion reaction? Is it going to be 6? You know, do I add these together? 4 liters from this, 2 liters from that? Do I add them together? No. Is it going to be 4 liters or is it going to be 2 liters?
2 liters.
It's going to be 2 liters. Because once all the oxygen in the air is used up, there's no more oxygen left. It's a sealed container. Does that make sense?
Yeah.
And so the theoretical yield, this is what we call the theoretical yield. And what would be the limiting reagent?
10 liters of air.
Yeah, this is the limiting reagent. And what would be the excess reagent?
5.8.
This would be the excess reagent. Now, I didn't put enough air in there. 10 liters wasn't enough. And so what we need to do is this. Let's figure out how much leftover glucose remains. So can you calculate the grams of excess glucose remaining? This wasn't combusted. So we got to burn what we've